As computer designers, we are often faced with various design questions. Is one design option better than the other? We need to be able to answer these design questions in a quantitative fashion by quantifying the performance implication of each design option. And that is the topic of this video. First, let us identify who are the set of people who care about computer performance. What are the different categories of people you think care about computer performance? The set of people who worry about computer performance fall into at least three categories. One is the customer who uses the end computer. Next is the vendor who is trying to sell the computer. And the third category is the computer designer. We are computer designers, and it is from this perspective that we will be looking at computer performance. Now, what are the possible metrics of computer performance you can think of? In fact, before you think of computer performance metrics, let us think of the performance metrics of, let us say, a courier service. When you choose one courier service versus another, what are the various aspects of performance you will be considering? Likely, you will primarily be worried about the time to deliver. You will also likely be worried about reliability in terms of the fraction of times in the past they have failed to deliver, or the fraction of times in the past they have delayed your delivery. The next important metric would be cost per unit weight, and perhaps you will also be worried about what is the maximum weight this courier service is allowing to carry. Maybe you will also be worried about factors such as delivery confirmation. Another factor could be whether they have an online tracking facility, number of destinations on offer, whether they have a pickup service at your address, and so on. So clearly, there are a whole range of metrics which can be measured to quantify the performance of one courier service versus another. So let us now come to computer systems. So who is the customer in a computer system? The customer in a computer system is essentially the one who is executing programs using the computer. So what metric does the customer care about? The primary metric the customer cares about is the execution time or the response time. There is another metric as well which typically the sysad will care about, the one who is managing the computer. The sysad will also care about the throughput or the number of programs which can be executed per unit time. Each customer is of course concerned about only the execution time of the program that customer is executing. The sysad is concerned about the throughput involving all of the programs. The notion of throughput is especially important in a multi-user environment. In this course, we are going to be primarily concerned about this metric of execution time. We are going to be essentially considering a system which has one executing program at a time. In this context, the execution time metric is the one which is more relevant than the system throughput. Now, in a Linux environment, you may have used the command time to measure the execution time of an executing program. So let me show you an example here. Here I want to execute this program find, which can be used for finding files. I want to find this particular file. This is a command. Now if I prepend time, this time program executes the other program find and also summarizes the time taken for that particular program. And here is the output. It gives different components of the execution time. The first line here is the total time taken. The time taken by the instructions corresponding to the program is given here. And there are also some system commands which are run on behalf of the program. And this last line gives the time taken for those. So now we have decided upon the metric for computer performance, and that is the execution time. So how do we measure the program execution time? Most computers are implemented as a digital circuit, as a sequential circuit. When you talk about a sequential circuit, you have the notion of a clock, and there is a clock frequency and the number of cycles of the clock. So program execution time is easily given by the number of cycles of execution times the clock cycle time, or the number of cycles divided by the clock frequency. It is convenient to write this particular computer performance equation in terms of three components as shown in this last line here. The component of clock cycle time remains the same as from the previous version. The number of cycles, we can break it down into number of instructions which are actually executed and the number of cycles per executed instruction. This is the average across all executed instruction. The keyword here is executed instructions and specifically not the number of static instructions in the program. There is an easy way to remember this particular computer performance equation. The time taken per program can be viewed as instructions per program times number of cycles per instruction times time taken per cycle. We will next see the usefulness of this particular computer performance equation through various examples. So here is our first example of the use of the computer performance equation. We saw earlier that MIPS does not support the BLT instruction, branch less than. At some point of time, the designers of MIPS would have been faced with the question of should this instruction be supported? And this example gives an idea of how they may have gone about answering this question, although the numbers given here are hypothetical. The two options here are yes, MIPS should support the BLT instruction, and the other option is no, it should not support. Both of these have implications. If you go with the option of supporting BLT, it results in a 20% higher cycle time. And the implications of not supporting are that in this particular program, which is run as a test case, let us say that 10% of instructions are BLT. They essentially need to be replaced with two instructions, that is SLT followed by BEQ. So given these numbers, you can answer the design question quantitatively. Give it a try. So here is the solution. If we denote the clock cycle time by T, the first option has 5 million instructions and some particular CPI and 1.2 times T as the cycle time. The execution time with the second option would be 5.5 million instructions times the same CPI times T. And if you do the math, you'll easily see that option B of not supporting BLT instruction is faster. Here is a second example of the use of the computer performance equation. Let us say a hardware designer is considering two possible implementations of the same instruction set. In the first implementation option, the clock cycle can be 2 GHz with the CPI being 1.5, and in the second implementation option, the clock cycle can be increased but potentially with the penalty that the number of clock cycles per instruction increases to 2. Well, we want to know which implementation option is faster and by how much. If you do the math, you will figure out that option 2 is faster and by this factor. Let us consider a third example of the use of the equation. Intel instruction set supports add operation in which one of the operands can be a memory location. Now, a hardware designer is considering two options for implementing this particular instruction in the instruction set. One option, indicated as option 2 here, is to have additional hardware support whereby the number of cycles for add remains the same, however the cycle length increases by 10%. Another option he is considering is to implement add as 3 cycles. This will retain the cycle length as the same but will increase the number of cycles for a particular program from 2 million to 2.4 million. Which of these two options is better and why? If you do the algebra using the same equation, you will find that execution time in option 1 is as given here, where T is the original cycle length, and execution time 2 is also as given here. And given this, it's easy to see that the implementation option 2 is the faster one. There are 3 factors in the computer performance equation: the number of instructions executed, the cycles per instruction average, and the cycle time. How are we going to measure each of these components? Of these 3, cycle time is the most straightforward to measure, that you get directly from the inverse of the clock frequency. As mentioned earlier, the number of instructions is the number of executed instruction, which means you cannot get this from a static count. You have to use techniques such as profiling, or if you have an instruction set simulator, you can get the number of executed instruction. The other option is to have some hardware counters, using which you can get the actual number of executed instructions during the execution of a program. The CPI can be calculated if the instruction mix is known. Instruction mix is nothing but the different fractions of the different types of instructions. The different types of instructions could be arithmetic, memory, branch, and so on. Typically, the hardware implementer will know from the hardware implementation as to what is the number of cycles taken for each type of instruction. For example, in a particular hardware implementation, memory instructions may take 2 cycles, arithmetic instructions may take 1 cycle, and branch instructions may also take 1 cycle. So the CPI, cycles per instruction, is known for each type of instruction, and once we know the instruction mix or the fraction of instructions, fraction of executed instructions of each type, then we can compute the average CPI from this simple formula, which is a weighted average of the CPI of each instruction type. As a simple example, let us say that memory instructions have a CPI of 2 and the percentage of executed memory instructions is 25%. So the CPI will be 0.25 times 2, and let us say that the rest of instructions all have single cycle implementation, that is CPI is 1. So the average CPI will then be 1.25. Given the computer performance equation, which has 3 components, number of instructions, CPI average, and the cycle time, different factors could affect each of these 3 different components. Clearly, one factor which affects the performance of a program is the underlying algorithm. Which of the 3 components in the computer performance equation does the algorithm affect? Another factor which affects the performance of the program is the choice of the programming language, the higher level language, which is used for coding that particular program. This factor of programming language, which of the 3 components does it affect? Another factor which can affect the performance of a program is the compiler. Which of the 3 components of the computer performance equation will the compiler affect? The instruction set architecture clearly affects the performance of the program. Which of the 3 components does the instruction set architecture affect? And finally, the hardware implementation will also affect the performance of the program. Which of the 3 components will the hardware implementation affect? So here is the summary of the factors affecting performance. The choice of algorithm mostly affects the number of instructions. It can sometimes affect the CPI. For example, it is imaginable that an algorithm can affect the number of arithmetic additions versus the number of memory access operations, which will affect the CPI. The choice of programming language will affect not only the number of instructions but also the instruction mix, which affects the CPI. Compiler has a very huge effect on both the number of instructions as well as the instruction mix. The instruction set architecture is something which affects all 3 components of the computer performance equation: the number of instructions, the CPI, as well as the cycle time. The hardware implementation itself has little to do with the number of instructions. It, however, affects the other 2 components, CPI and cycle time, of the computer performance equation. As mentioned just now, the compiler can affect the performance of the program. Here is a hypothetical example illustrating the same. Let us say that the CPI for different kinds of instructions is as given. For branch instructions it's 2, for memory instructions load word, store word, it is 3, and the CPI for other register instructions is 1. The compiler is considering 2 options for translating a higher level language code segment into assembly language. In code sequence 1, there are 8 branches, 8 loads, 2 stores, and 8 register, and different sets of numbers for code sequence 2. In this situation, which code sequence is better and by what factor? You can use the same computer performance equation to determine that the execution time in the first case would be as given here, and the execution time in the second case would be as given by the second equation here. So the first option is faster by a factor of 10 over 9. We have so far sidestepped this important question of which program to use for performance analysis. We've been saying number of executed instructions, but for which program? Clearly, the result of the performance analysis may vary depending on which program you use for the performance analysis. We have the notion of a benchmark or a specific program which is used for such performance analysis. A question in this context is, should the benchmark be a special program or should it be a real program? If real program, what real program? There are, after all, a wide range of real programs which we use. After much deliberation and experience, the industry has come up with this SPEC benchmarks. SPEC stands for System Performance Evaluation Corporation, which has been in existence since 1989. In the textbook, you can find the programs which are present in the SPEC 2000 benchmark. These benchmarks are really a collection of programs. This collection includes various programs which we use in real life, such as gzip or GCC, and it also includes various scientific programs, various programs which are heavy on floating point operations, and so on. So it is common to do performance analysis not in terms of one program, but in terms of a benchmark, which is a collection of programs. When we are doing performance analysis of different computers or different design options for the same computer, we need to summarize the performance analysis. One thing to keep in mind as an engineer when you summarize performance is to think in terms of reproducibility of the results. That is, you must give enough information for another person to look at your performance analysis and reproduce the results if necessary. For example, if you are using a benchmark and if you are summarizing the performance of each of the programs in the benchmark, you must specify what input you gave to each of the programs when you conducted those tests. In the context of computer performance, an intuitive observation goes by the name of Amdahl's law. It can be stated as the performance improvement that you achieve is limited by the fraction of the program that you are actually improving. To explain this, let us say that this represents the execution time of the program, and there is a fraction f which you are improving, and there is a fraction 1 minus f which you are not improving. Let us say the improvement factor is n. The execution time now becomes f by n because the fraction of the program you have improved is f, and that becomes f by n. But the 1 minus f part remains as it is. So the overall improvement is 1 divided by 1 minus f plus f by n. So the intuitive observation is that this is always less than 1 by 1 minus f. So however much you increase the factor of improvement n, if f happens to be small, your overall improvement is going to be small. This is the intuitive observation captured by Amdahl's law. Here is an example application of Amdahl's law. Let's say that Intel wants to improve its CPU chip and it's considering two options exclusive of one another. The first option is to speed up memory by a factor of 10, and the second option is to speed up ALU, arithmetic logic unit, and it is able to do it by a factor of 2. To answer which option is better, we need to know the fraction of instructions executed in each category. Let's say that the fraction of ALU instructions is half, fraction of memory instructions is 0.2, and the other instructions is 0.3. So which of these two options is better? If we do the arithmetic, we will find that the speed up in the first case is about 1.22, 1 over 1 minus 0.2 plus 0.2 by 10, and in the second case it would be 1 minus half plus half by 2, which is the factor of speed up here, and this would be 1.33. So clearly the second option is better. So we see that even though the first option gives a factor of 10 speed up, this speed up is only for a small fraction of executed instructions. So overall the second option for speed up is the better one. To summarize what we have seen in this video, it is important to quantify the performance of programs. For as engineers, we need to answer design questions quantitatively. We have seen execution time as the primary metric of such quantification. We have seen the role of benchmark programs for quantifying performance, and we encountered Amdahl's law, which essentially states that not only is the factor of speed up important, but also the fraction of program which you are speeding up.